Hello, this is video number 31 from Multivariable Calculus course. In this video, we're going to talk about Stokes Theorem. Stokes Theorem relates a line integral of a vector field with a surface integral. So imagine you have a surface and the boundary of that surface is a curve. So it cannot be a closed surface. So I'm going to call the surface sigma and I'm going to call the curve C. We want to relate a surface integral over sigma and a line integral over C. We have had something similar to this in two dimension. The two-dimensional version of this one was called the Green's theorem. That told us if we look at a region R whose boundary is positively oriented, which means that if it is outside, it would be counterclockwise. If it is inside, it would be clockwise. Then there's a relation between a line integral m dx plus n dy over this curve and a double integral over the region nx minus my dA. So this is in two dimension. In three dimension, we want to relate a surface integral over sigma and a line integral over C. But before we can do that, we need to have orientations. So there are two orientations for sigma. The orientation, if you recall that orientation, was a collection of normal vectors. The orientations for this sigma in this diagram could be either upwards or it could be downward orientation. We also have two different orientations for the edge or boundary of this sigma. The orientations could be clockwise or counterclockwise when viewed from above. Note that since we are dealing with the curves in three dimension, just saying clockwise or counterclockwise doesn't make a lot of sense. So saying clockwise or counterclockwise would always have to come with which direction we are looking at the curve. So the orientation of sigma that matches an orientation of C is the one that matches the right hand rule. So if you look at this orientation of C, that matches the up orientation of sigma pointing upwards. Now the other orientation that is downwards for sigma would match this orientation of C. So these are matching orientations. We say these are positive orientations. So the green ones are positive orientations and the black ones are also positive orientations. So positive orientation is in relation to another orientation in this case. So as an example, we had like a hemisphere. So orientation upward would be along with orientation counterclockwise when viewed from above. Okay, so now what does that in fact tell us? What does the Stokes theorem tell us? The Stokes theorem tells us that if you look at the positive orientation, then the surface in the line integral of f dot dr over this curve is equal to the surface integral of a curl of f dot n ds. So this is what this Stokes theorem tells us, assuming that the orientation is positive. So now we will do a few examples on this. So the first example is let C be the triangle with vertices 0, 0, 0, 1, 0, 0, 1, 1, 1. So we're going to graph this one first. So it's a triangle. The vertices are the origin and 1, 1, 1 and 1, 0, 1. So let's draw that. So the origin 1, 0, 1 and some point in the first octant 1, 1, 1. So this is our triangle, and it says oriented clockwise when viewed from above. So when you look at that from above, the orientation is clockwise. So this is the orientation. And the question is asking us to evaluate this line integral. Now, if we were to evaluate this one using the direct computation or the definition, we will have to have three parameterizations for this curve because this curve is a combination of three different segments. So we'll have to do this line integral 3 times. Instead, what we are going to do is we're going to choose a surface whose boundary is this curve C, and use Stokes theorem. So if you look at this triangle, what is a surface whose boundary is this? Well, that surface would be the inside the triangle. So let's call that sigma. So let sigma be the triangle bounded by C. Now we need an orientation. We need an orientation that follows the right hand rule. So the orientation that follows the right hand rule would be downward. Oriented downward. So given that, we can apply the Stokes theorem. Our vector field F is going to be y plus x cubed I plus y cubed j plus z cubed plus 1 k. This is our vector field. So we can apply the Stokes theorem. So Stokes theorem tells us that the line integral over this curve, so the line integral of f dot dr is equal to the surface integral of a curl of f dot dn ds. Okay, so for that, we need to find the curl of this vector field. So let's evaluate curl of this vector field. Curl of the vector field, as we have learned before, is the cross product of the nabla, partial with respect to x, partial with respect to y, partial with respect to z, and f y plus x cubed, y cubed, z cubed plus 1. Eliminating the first column, we get 0 minus 0i. Eliminating the second column, we get 0 minus 0j. And finally, eliminating the last column, we get 0 minus 1k. So negative k is our curl. Okay, so this would be double integral, surface integral of negative k dot n ds. So to evaluate this surface integral, we need to have a parameterization for our surface. So we need to parameterize the plane. So how do we parameterize sigma? Sigma is a plane. So we'll have to find two vectors inside that plane, and we have to find the normal vector to the plane. So if I call these points maybe A and B, and I already have the origin, I can find two of these points, maybe OA, two of these vectors and OB, and then find the cross product of these two vectors. So what is OA? OA is 1, 0, 0. What is OB? OB is 1, 1, 1. And then we're going to have to find the cross product of these two. 1, 0, 0, 1, 1, 1. Eliminating the first column, we get 0 minus 0i. Eliminating the second column, we get 1 minus 0j. And eliminating the last column, we get 1 minus 0k. So this would be minus j plus k. This is a normal vector. So sigma becomes the plane containing this normal vector. So negative 1 times x minus, well, y minus 0, because 0, 0, 0 is in this on that plane. So let me actually start from the first component. The first component is I, which is 0, x minus 0, minus y minus 0, plus z minus 0 equals 0. So the graph of this plane is given as z equals y. Now we can parameterize this one by r of xy equals x comma y comma y. But now what are the limits for x? Well, we can project it onto the xy plane. Onto the xy plane, the projection would be the origin stays the origin. 1, 0, 0 becomes 1, 0. 1, 1, 1 becomes 1, 1. So this is the projection onto the xy plane. Now we can set the limits of x and y. Y goes from bottom of 0 to the top of x, and x goes from left to right, 0 to 1. So now we can set up the surface integral. So Rx cross Ry, which is the normal vector, is negative fx. So we had a formula for that. We talked about a formula for this one. This is f of xy, negative fx, which is 0, negative fy, which is 1, and 1. So this is the normal vector. But then we have to check the orientation. This is upward. So since the orientation is upward, we'll have to use negative of this one. So we'll use 0, 1, negative 1. And if we do that, the surface integral of negative k dot n ds becomes the integral over this region R. So let's call this region R of negative k dotted with this vector, which is 0, 1, negative 1 ds, or dA rather, because we're going to two-dimension now. Now the integrand is going to be the dot product of these two. Dot product of negative k and j minus k would be 1. So this would be 1 dA over R. And that's exactly the area. So this is area of R. But R is a triangle. Base and height are both 1. So the area is 1/2. So that is our answer to this problem. Okay, so let's look at another example. Let sigma be the ellipsoid x squared plus 4y squared plus z squared equals 1. So we're going to graph this one above the xy plane. So it's only part of it that is above the xy plane. So we have the intersection with the xy plane would be an ellipse, of course. So it's an ellipse. And then it's only the top portion of this ellipsoid. So this is our sigma. And the orientation is upward. So this is the orientation of this ellipsoid. And we are trying to find the surface integral of curl of this. Now, there's in fact two different ways of doing this problem. So I'm going to do this in two different ways. The first one is we evaluate the curl. Let's evaluate the curl of this vector field and see what we get. So curl of f is going to be I, j, k, partial respect to x, partial respect to y, partial respect to z. So I component is x, y, and the last one is z sine of xy. So the main problem with evaluating the curl and trying to use the direct computation is that parameterization of this ellipsoid is going to be a little bit challenging. Instead, there are two different approaches that we can take. First, let's make sure that we know what the boundary of the surface is. The boundary of the surface is this curve C, and the orientation would have to be done using the right hand rule. So this is the orientation of the boundary. Now, if we evaluate the curl, we see that the curl is eliminating the first column. We get z x cosine of xy minus 0 I minus, eliminate the second column, we get z y cosine of xy minus 0 j, and eliminate the last column, we get 0 minus 0 k. Now, one thing that we notice is that this curl doesn't have the k component. The k component is 0. Now, if we look at the bottom of this, this is also another surface. I'm going to call this one sigma 1 with the same boundary. So instead of evaluating the surface integral of a curl over sigma, we can also evaluate the curl, or a surface integral of the curl over sigma 1. So I'm going to orient that upwards as well. And I'll explain what I just said. So let sigma 1 be inside the ellipse x squared, the ellipse that they gave us on the xy plane, on the xy plane. So going back and looking at what we had x squared plus 4y squared plus z squared equals 1. Bottom becomes x squared plus 4y squared equals 1. That's the curve. So let sigma 1 be inside this curve oriented upward. Now, we will apply Stokes theorem. So Stokes theorem tells us this. Stokes theorem tells us the surface integral of a curl of f dot n ds, which is what they gave us. They gave us the surface integral of curl dot n ds. That's equal to the line integral of f dot s or dot r. This is what Stokes theorem tells us. Okay, we can also apply Stokes theorem again. If we apply Stokes theorem again, we can change our surface to something much simpler. So we could say the line integral over c f dr is the same as the surface integral over a different surface. This time a simpler surface. It is just the bottom surface right here, the ellipse. Now, if you notice, what is the normal vector? Well, the normal vector to the plane is a multiple of k. So n is a multiple of k. Now, if you look at curl of f does not, based on the computation that we did, does not have k component. So what does it mean? It means the dot product of these two is 0. So curl of f dotted with n is just 0. So what does it mean? It means the line integral of f dot dr is going to be just 0. Or rather, the surface integral would be 0, which means the line integral would also be 0. So the surface integral of curl of f dot n ds is going to be 0 because the integrand is 0 because curl is perpendicular to the normal vector. And once this is 0, that means the surface integral of a curl over the original surface is also 0. So the answer is in fact 0. So that's one way of doing that. The second method would be to use the line integral. So this is solution number 2. So what we can say is that we could say the surface integral of curl f dot n ds is equal to the line integral of f dot dr. And then we can use the parameterization of the ellipse. Because it's an ellipse and because the orientation is counterclockwise when viewed from above, the ellipse theta would go from 0 to 2 pi. So what are the values of x and y? X is cosine of theta, y is 1/2 sine of theta, and theta ranges from 0 to 2 pi. So we can take that, evaluate f at these points. So f would be cosine of theta I plus 1/2 sine of theta j plus it is z sine of xy and z is 0. So that would be 0k dotted with the derivative. The derivative is derivative of cosine is negative sine theta. That's r prime. And then 1/2 cosine theta and of course 0 d theta. And once we evaluate this, we get cosine theta sine theta, and there's a negative sign, plus 1/4 sine theta cosine of theta, d theta. And this is if you do a substitution for cosine or sine, you end up getting 0. So you could do this with u equals cosine of theta or u equals sine of theta. Either way, it gives you the same thing. Okay, so we could do this one in two different ways. Let's look at one more example. on Stokes theorem. Let sigma be part of the cylinder x squared plus z squared equals 1. So x squared plus z squared equals 1 between y equals 0 and y equals 1. So this would be our surface. And orientation is outward. So this is the orientation. Along with the disk, this disk, x squared plus z squared less than or equal to 1 on the xz plane. And the orientation is to the left. So this is the orientation. So you see like these two orientations match. All three orientations are outward from the cylinder. And we want to evaluate the surface integral of a curve. So now, again, we could do two different things. We could either find a second surface with the same orientation, or we could find the line integral over the curve itself. I will choose the second surface, but both of these methods would work. So we can choose this surface that has the same boundary. So let's call this surface sigma 1. It would have to match the other surface, the orientation of the other surface. So it would have to go this way. And then we have to choose an orientation. So the orientation that would work with the right hand rule would have to be this way. So this is going to be the orientation. So what we can do is we could say by Stokes theorem, the surface integral of curl of f dot n ds is equal to surface integral of, or let me write down the kind of the connection here. The connection is if you call this curve C, we would get line integral of f dot dr over C. That's the Stokes theorem. And that's surface integral of curl of f dot n ds. So we are applying Stokes theorem twice. Once here and then once here. Okay, so now we can evaluate curl, and again you could also apply using the formula for line integral. Either one of these two should work. Okay, let's now look at the surface integral. First we have to find the curl, so let's evaluate the curl of this. And notice that because it's a plane, sigma 1 is a plane, the I and k component do not matter because normal vector is in the direction of the y-axis, negative y-axis. So the I and k component don't actually matter. I'll evaluate them, but they don't actually matter. So I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, z plus 1, y squared, and minus z plus 1 xy, and finally e to the x squared y squared. So this is equal to, eliminating the first column, we get derivative of this one, which is e to the x squared y squared, times the derivative of inside, which is 2x squared y, that's the derivative with respect to y, minus partial with respect to z, which is plus xy I. Now again, we know this is not going to matter because eventually we'll have to find the dot product with n, and n is in the direction of the y-axis. So the I component doesn't matter. Fortunately, this is a little bit too complicated, so it's actually not going to matter. Minus partial of this with respect to x, which is e to the x squared y squared, times derivative of x squared y squared, which is 2xy squared, and then minus derivative with respect to z, which is y squared, j, and then plus partial with respect to x of this one, which is minus z plus 1 times y, and then minus 2z plus 1 times yk. So the I component and jk component do not matter. So let's look at the surface that we found. Sigma 1 is given by x equals r cosine of theta and y equals 1 and z equals, let me write it down, z equals r sine of theta. Okay, so it's going to be r of r theta equals r cosine theta 1 r sine theta. And because this was a unit circle, unit disk, r is going to be between 0 and 1, and theta would be between 0 and 2 pi. Next, we're going to have to find the normal vector and then make sure that the normal vector is pointing in the negative direction of the y-axis. So r sub r is going to be cosine 0 sine. R sub theta would be minus r sine 0 r cosine. If we find the cross product, we are going to get 0 for the first component. If we eliminate the first column, we get 0. If we eliminate the second column, we get r cosine squared theta plus r sine squared theta, and the last column would give us 0. So this would be 0 r 0. So this is to the right, so we'll have to negate that. So we will have to use negative 0 r 0. So we'll have to use this one. Now we'll find this curl f, the surface integral of curl f over this new surface. So we'll do that. So curl of f, we already evaluated that. Curl of f is this guy. And then if you find the dot product of this with, let's actually do the dot product first because I don't want to keep writing down this whole thing. So curl of f dotted with 0 negative r 0 is going to be, we can ignore the I component and the j component. We only need to multiply the, sorry, I component and the k component. We only need to multiply the j components. So it's negative r, and then for the j component we get minus e to the x squared y squared. X is r cosine and z is r sine. So x squared, y is 1. So we are looking at this one, x squared y squared times 2 cosine, so 2x, which is 2r cosine, times y squared minus 1. So this is going to be our dot product. So minus e to the power of x squared y squared 2x times y squared minus y squared. So that was the integrand. And then we'll have to integrate this from 0 to 2 pi for theta and from 0 to 1 for r. So it would be plus, the negative signs multiply and we get plus r squared 2r squared e to the r squared cosine squared theta cosine of theta minus plus r dr d theta. Okay, so this integral is a little bit complicated, but in fact it's not too bad if you swap the order of integration. If you swap the order of integration, we get integral from 0 to 1, integral from 0 to 2 pi, and it would be 2r squared e to the r squared. I'm going to change cosine squared to 1 minus sine squared. Cosine of theta d theta dr. And I'm going to do the other one separately. So integral from 0 to 2 pi, integral from 0 to 1, r dr d theta. Now we can do this one by u substitution. This one can be done by u equals sine of theta. If you substitute u equals sine of theta, its derivative is right here. And this integral becomes 0. And this one is an easy integral to evaluate. So to summarize, we talked about this Stokes theorem, which tells you a relation between a line integral and a surface integral. And we saw 3 examples of Stokes theorem. If you have 2 surfaces that have the same boundary and the same orientation, then the surface integral of curl is the same over these 2 surfaces. I will see you in the next video.